everybody. Welcome to my presentation. So we've got a very long title, but just to make it short. So I'm interested in working with time series, data ordered in some kind. So for example, sensor data. But everything which is ordered, like for example, reflection spectra or events in the process sequence would also qualify as time series. Now what I want to talk about is systematic time series feature engineering. So how can we remove the tedious part of manually constructing features from time series, and of course use these applications. From the engineering point of view, what I want to do is I want to automate decisions on time series, on streaming data, for example. Now, the example I'm going to talk about here is a collaboration with the Department of Electrical Computer and Software Engineering. We want to detect sensors, and we want to detect if the sensor has broken down, has a failure, if we have never seen a specific failure before. For example, think about a new sensor system which has been constructed. It's a very cheap sensor. You want to deploy it in the field, and you know it will break down at some point, but you don't know how this breakdown will look like in the data. Now, the typical situation is that if this is a wireless connection, that sometimes you won't have enough all data points, so the transmission will be interrupted at some point. And if a sensor has broken down, you want to transmit the data from the edge layer into the cloud layer. So you just want to shut out the defective sensor from any further transmissions. Now, what this would look like, so this is an example toy set from the Intel Berkeley Research Lab. So these are indoor sensors measuring temperature over time. And usually, in an engineering context, we can afford the engineer to be on site for a couple of days, calibrate the system, and then let it go, right? So here we assume we just have the test train set. It's just 10% of the data, and the further test set will be 90% of the data. So we inverted the normal methodology, and as we know, temperature is expected to be between 18 degrees, maybe 28, but certainly not 40, 50, it's not an oven, right? So we don't bake our office stuff. But what's happening is, can an AI learn what is normality and then flag a sensor as being not normal anymore? And this, of course, is a toy example, and it's very easy to spot that something is out of the order here when the sensor, the temperature rises, the battery might be flat or whatever. But the question is, can we automate the process of learning normality and flagging everything which is not normal? Now, the basic idea is, typically in machine learning, we would use naive feature engineering. Naive feature engineering is when we just use the streaming data itself, maybe remove a little bit noise, just some signal processing, but use the raw data. So every row here is a sequence of measurements over a window. And this is naive feature engineering, so the algorithm has to learn how to represent this data and learn the characteristics for the problem itself. Now, in systematic time series feature engineering, we basically use a kernel trick and project the data, every window, every sample of the time series, into a feature space. So we've got a couple of functions from a library, which are chosen from different fields of research. So from signal processing, statistics, time series forecasting, financial time series analysis, and nonlinear dynamics. So all kinds of features which have been proven to be useful in some kind of time series classification or time series regression project. Now, having this feature space is nice, but which of these features just contain noise? So we need to do some kind of feature extraction or selection. So univariate selection in combination with multivariate works best. But where to get the labels from? So the idea is, from this short training set, we choose basically a rolling window approach, and we select those features which are able to predict a statistic of an adjacent future window, right? So we create our labels for feature selection from the streaming data of the short test set, and then we combine the feature extraction using the TS-Fresh library together with univariate and multivariate feature selection. So what works best most of the time is something like random forest regression and recursive feature elimination. And then we get a model for each sensor individually, which describes its normality. And if we do this over a sensor network, we find that, that some features are appearing again and again. And this means we basically have captured some features, some characteristics, which can be used for describing normality. And then classical unsupervised learning, here it's just a PCA model, where normality would be located around the origin, and the blue dots here from the training set are at the origin. Everything which is green is dotted overhead. And we see clearly that those outliers here, right, then are far away from the origin. So choosing a suitable distance from the origin, we can detect any outliers even if we have not seen them before. Of course, choosing the threshold is an issue, but so here we just have used the sensitivity of the algorithm, but if we use local outlier factor models, we can automate even the threshold and understanding how many features would be suitable if we do out-of-sample testing on different sensors. We found that depending on the data set, so the top one is the Berkeley data set, it's indoor, it's quite easy, but for outdoor data it's more complicated, but we get quite a good detection of errors, even if the model never has seen errors before. So have a look at this paper in IEEE Census Journal. Might be useful to combine this with your approaches and using systematic feature engineering. Thank you.